I suspect that for most people, thinking of transformations inspires and invites images of frogs all of a sudden being transformed into Prince Charming, or if you're a really pessimist, maybe of Prince Charming switching back to being a frog. But this is not what we're going to be looking at for this class, because of course this is a linear algebra class, so we're going to be looking at transformations having to do with linear algebra objects such as matrices. What we are going to do is we're going to see how each matrix can be used to define a function, and that's really what the transformation is all about, that will in fact transform things, but it will transform vectors from one into the other. So the idea is the following. Let's say that we have a matrix. It doesn't matter how big of a matrix, so general m by n matrix. We're going to define a function. I'm going to use some notation that probably you're not too used to, although you should have seen it in calculus at some point most likely. But we're going to define a function, and really transformation is the linear algebra word for function, okay? Except that, as we're going to see soon, functions or transformations, that is functions in linear algebra, have some very special properties that they do not have for regular functions in calculus. So what functions are we going to look at? Well, we're going to define a function that we will call L sub A, L for linear, sub A for it's associated to the matrix A, and it's a function that takes a vector in Rn, so an n-dimensional vector, and changes it to an m-dimensional vector, or of course the n and the m are the same as the dimensions of the matrix. So what this function does is it takes a vector, which is an n-dimensional vectors, and it changes it to another one. Which one? Well, simply the product of a and x. So remember, A is going to be an m by n matrix, and x is going to be an n by 1 vector or matrix, and the product will give us an m by 1 matrix, that is an m-dimensional vector. All right. So this thing again is called a matrix transformation or a linear transformation. Matrix transformation, well, I hope I don't have to justify why. It's done by using a matrix. Linear transformation, hold on to your hat. I'm going to explain to you very shortly why it's called the linear transformation. In fact, that is going to be the most important thing we're going to see in this class. Let me give another way of looking at this situation. So we start from this matrix, m rows, n columns. This matrix will be used as the tool to define this function. How does the function work? It takes a vector, an n-dimensional vector, multiplies it, and ends up with another vector, which is an m-dimensional vector, therefore in Rm. Okay? And that's all basically. It's the operation we're doing is something we've been doing very often, and so you should be very familiar with it. It's just a matter of figuring out what are the properties of this kind of transformation or function. As traditional in linear algebra, let me give you some more jargon words which are associated with this whole idea of matrix or linear transformation. So if we start from a matrix transformation given by some matrix A, then the space Rn, which is the one that we're starting from, is the domain of the transformation. Notice that unlike functions that we've seen in calculus, for a matrix transformation, once it have the matrix A, it can be applied to absolutely any vector in Rn. So there are no restrictions on the domain. So the domain is just, well, which vectors can we use, and once we know which ones they are, we can use them all. Then we say the space Rm, which is the space of vectors that we're going to get out of it, or the space in which we find the vectors that are going to come out of the transformation, is called the codomain. And this is a word that probably you have not seen, because for functions, generally the codomain is always the set of real numbers. So what this transformation does is it takes an element x, a vector x in the domain, and changes it to some vector y in the codomain. So just like in regular functions, we can think of y as being a function of x, except it's a very specific function, and it works on vectors, and it works on vectors through a matrix. Now, if we start from each vector x, from a vector x, what we obtain from x by multiplying by a is called the image of x under the linear transformation. And now what we can do is we can look at the set of all the images, okay? And this is what we call the range, just like in calculus. So the range of a linear transformation is the set of all vectors that we obtain as images of vectors in the domain.